Okay, so this is lecture 21st. This is the lecture progress. So we are at the lecture 21st, and currently the coverage is around lecture 19. So 2 lecture hours behind, but since we have 2 remaining lectures, recorded lectures during my business trip to Kyoto, so I think that it's completely okay to cover these materials. So I think that the last parts are just optional. So I think that it's better to cover those materials more deeply in the real lecture, offline lecture. Okay, so let's go to today's lecture. Today we will just finish our previous contents on some effect related to the hot electrons, and also related to the reliability. So these are actually very important in practice for developing the real technology, but not much covered in the undergraduate level. So let me just briefly introduce some discussion or some short note on those topics. Okay, so let's go. So in the previous lecture, I just directly dive into the main the content of our first one. So in the previous lecture, we have considered the concept of a hot electron. Maybe you remember that condition. So of course, hot electron means we are considering M MOSFET. If we consider P MOSFET, then we must consider hot holes. Here, hot means that they have sufficiently high kinetic energy, so they are far from their minimum energy values. For example, when we consider a certain electron, we can think about its energy. Yes, it can have an energy, and its energy can be decomposed into two parts. One part is the energy of that electron in its energy minimum. So this is corresponding to the conduction band minimum, and also kinetic energy. This is the related to the velocity. So when we say an electron is hot, it means that actually this kinetic energy is much larger than number 0. So we have sufficiently high kinetic energy. What is high and what is low in this case? Well, think about this one. 0.02 eV electron volts. Then do you expect that this is hot or cold? So since this is more or less corresponding to just kBT, thermal energy, so this one is just regarded as cold one. So we don't think that this is a hot one. However, think about this one. If this kinetic energy is orders of 1 eV, 1 electron volt, 2 electron volt, 3 electron volt, blah blah blah. In this case, we can certainly say that these numbers are just at least, for example, when we have just 1 eV, this is corresponding to 40 times over our kBT. So it is really improbable to have such a high electron energy in terms of kinetic energy. So this one is regarded as a hot electron. So as I told you before, not every electron is hot, even when we operate in this condition. For example, say that we apply just 0 volt to our source source terminal and say we apply very high voltage to our drain terminal, then starting from this source end of our channel, after this journey is over, then the maximum energy we can expect from this journey is simply given as positive Q times VDD. This is the maximum amount we can expect from the journey of electrons from source end to the drain end. Why? Because in this case they have different energy levels. When we draw their conduction band energy level, there is certain difference corresponding to Q times VDD. So therefore, if it does not experience any scattering event, then what we can expect is, after the movement of this electron is over and it is not scattered at all, then the energy itself, the total energy itself is preserved, conserved. However, now in this point, some of its original potential energy is transferred to the kinetic energy and it becomes really an hot electron. So this is the case. Of course, I'm not saying that always every electron just to keep its original energy. This is really a rare case. So in many cases, during its movement, there happens a certain event called as scattering. So it loses its energy, and it loses its energy, and again, and even when its journey is over, maybe the probable energetic point is just around conduction band minimum. So this is the movement of usual electrons, so majority of electrons. However, we can think very lucky electron which never experience or just experience one or two scattering event, so it does not lose its original energy much. So in this case, they are lucky and they become a hot electron. So therefore, what I wanted to say, stress in this context is this quantity. Please have a look at this quantity. So here I introduce a English small letter alphabet F. So usually, this F in our context is used to what? Used to describe, for example, Fermi-Dirac distribution or Maxwell-Boltzmann distribution. So it's a physical meaning. What is it? When it is approached to zero, then we believe that certain energy state is just empty, and when it approaches to number 1, then it is corresponding to that electronic state is almost fully occupied. So quite similarly, we can define a little bit more generalized quantity called as energy distribution function. So F. Of course, once again, it has the range starting from 0 and ending at 1, and 0 means that this state is almost empty, and 1 is corresponding to almost a fully occupied state. Then certainly you may ask me this question. Already we have Fermi-Dirac distribution. So what is the difference between Fermi-Dirac distribution and this distribution function? So Fermi-Dirac, in the case of equilibrium, just to well describe the occupancy of any electronic state. But what is the difference? So the difference comes from my short word equilibrium. So Fermi-Dirac function, distribution function, is valid only at equilibrium case. So if we go to non-equilibrium cases, so so in this case we cannot define actually Fermi level. Once we can define Fermi level, then we can define Fermi-Dirac distribution for certain energy level. However, in general, it's not possible. We have to consider non-equilibrium case. For example, let's say that we apply VDD to our drain. So current is flowing. So can we define the Fermi-Dirac distribution function over our device? So it's not possible. However, if we just generalize this concept, then now we can define this distribution function, which is typically a function of position, so real space, and energy. So now at a certain position, we can define different distribution function. Please note that Fermi-Dirac distribution is not a function of a position. It was a sole function of only energy level. Once the Fermi level is fixed, then that was the concept. This is a global quantity. However, now we introduce a localized position-wise quantity. Please think about this one. So let me just think about this one. Maybe it would be a little bit difficult for you to understand this concept. So let me just draw a simple diagram. So this is quite a typical case we can see in our N MOSFET. So say this is corresponding to the source terminal and drain terminal, and you can see that there is a difference. It's a minimum energy levels. Why? Because we have applied certain drain voltage. So this energy difference is corresponding to Q times VDS. For example, if we apply 1 volt to our drain, then we have 1 EV difference. It's energy levels. So question is quite simple. Think about a certain energy. Let's say that this is a certain energy. So please, then we can define we can think two different positions. One position is corresponding to the source, and another position is corresponding to the drain. Then I wanted to ask you this simple question. Then what is occupancy of this position? And what is the occupancy of this position? Please note that in this case, maybe since this is a highly doped source, maybe you can guess that your Fermi level is nearby this conduction band minimum energy. So are you with me? In this case, well, you may have the F value which is quite close to number 1. Not exactly number 1, but anyhow it is a meaningful value. Please think about this drain side. Where do you expect your local quasi-Fermi level is found? Do you still have a quasi-Fermi level, electron quasi-Fermi level nearby this point? Of course not. So since the doping density in this case is also quite high, your quasi-Fermi level will follow just the conduction band minimum value. So for this F value, so this position, now you can see that the distance, energetic distance between this cross point we are considering and its quasi-Fermi level is quite high. So it is certain that now we have almost vanishing energy, vanishing distribution function or occupancy in this case. That's the reason why we have to introduce this position dependency. At every position, our electron distribution function can be differed because quasi-Fermi level can be a function of a position. So at a certain position, our electrons are more highly occupied, and in other part, they can be less populated. So that's the reason why we introduce a little bit more generalized concept, position-dependent distribution function. Well, once we know this quantity, then actually in a semi-classical way, that's it. That means that this is the ultimate solution of our understanding on device physics. Once we understand this quantity, then people think that, well, now we have the complete information about device operation. So this is the very final quantity we wanted to get. To be more accurate, close to the final quantity, but anyway, quite close to the final quantity. So as I write down here, this is the quick quantity to understand various effects. So we wanted to know this quantity, but please be advised that calculation of this energy distribution function is quite complicated and computationally very difficult job. So that's the problem. If this quantity can be easily calculated, then everybody would be quite happy, but our job security is not that much high, because everybody can calculate this one, but this is really difficult to calculate. So in order to calculate this information, so simply what is this? This means that simply at a certain position and at a certain energy level E, how much the state is occupied. That occupancy is described by this distribution function. So the previous way, and still quite a usual way to calculate this distribution function, is shown here. See in this left figure. In order to calculate this this quantity, usually people adopt stochastic Monte Carlo method. Maybe if you are working with a circuit simulation, so circuit design, maybe you have heard about this Monte Carlo terminology once again in the SPICE simulation. But Monte Carlo terms called as Monte Carlo itself just means stochastic way to solve a certain problem. We just generate many random instances and just to observe their behavior and take certain statistical information out of it and try to get certain the underlying statistical information out of it. So that is the Monte Carlo method, and now you are looking at a typical way of solving the distribution function. So maybe you can see here certain trajectory. So this line is a trajectory of an electron inside a certain system. So this is position X and position Y. So now we are just looking at two-dimensional space, and we just insert our electron, and electron is now accelerated, and at this point scattering event happens. It certainly changes its direction, and after that still the acceleration is corresponding to this direction. It is anyhow accelerated once again and scattering, and once again accelerated, another scattering. When scattering happens, it has certain randomized velocity. So for example, even though acceleration is heading this way, after this event you can see that actually the velocity of this electron is just opposite direction because it just scattered. However, Although it starts from this direction, because there is a strong electric field, eventually its motion just follows this way. So therefore, in this case, we just follow the motion of an electron and randomly generate scattering event and just to see what happens to an electron. Wait, there was just one instance and number 2 electron, number 3 electron. If we introduce so many electrons, for example 1000 electrons or 10,000 electrons, million electrons, then what will happen? Each of them will show random motion, but when we just collect their average motion, then we can collect some good information about it. That is the way we do with this kind of information. So, for example, at this point, it has quite a high speed, and in this case, maybe it doesn't have quite a high speed. So, after long time later, we can make a certain tables or long Excel file. So, out of it, we can think about this one, this quantity. In average, when electron is here, it has a certain energy distribution. Also at this position, electron gas has a certain energy distribution. This quantity can be calculated. And the right one is an alternative way to calculate distribution function. So also we can calculate it by a certain computer program. Of course, this one is also computer program, and this one is also computer program, but in this case we do not use a stochastic method, just to try to solve it on deterministic way. And now you are looking at the distribution function. What is it? So please note that this is corresponding to number 1. It means that in this position or in this state, electrons are highly occupied. So please have a look at this number. This is corresponding to 10 to the minus 10. So there is just 0.1 billionth probability to be occupied by an electron. So lowly populated, for example. This is almost empty, and this part is almost fully occupied. And here we have a position and energy. If we have this graphs, for example, if I ask you certain question, at a position of 50 nanometer, please try to find out an electron whose energy level is given as 0. Then what you can do is just to make the cross point over these two numbers and try to find out certain values. Then you will have a certain number. It can be 10 to the minus 5, 10 to the minus 3, 10 to the minus 1, something like that. Then depending on its magnitude, then you may say that, oh, here we have almost no electron, or here we have many electrons. That can be understood. So actually, calculation of this quantity is a very long-standing research topic of modeling the electron transport inside our semiconductor devices. But please note that in order to calculate this quantity, we must solve Boltzmann transport equation, and unfortunately it is very notorious to be difficult to solve, or not impossible. So nowadays it is really possible, but we must spend a lot of computational burden. Okay, so anyway, so for example, frankly speaking, if you were born in 30 years ago, I would say that almost it is impossible to get this information. However, you are now, you were born about 30 years later than my expectation. So now even you can get this information relatively easily by certain means. So things are getting better and better. So simply speaking, many physical phenomena in our device physics or our course can be actually well explained by this distribution function. All kinds of techniques we are doing currently is the sole reason is it is really difficult to get this quantity. So that's the reason why we wanted to simplify it as much as possible. So also, in my opinion, the best way to simplify its this complicated distribution function is actually quasi-Fermi level. That's the reason why quasi-Fermi level is, or quasi-Fermi potential is so important. So please note that now you are looking at a certain distribution. Well, please fix a certain position. Your R is now fixed to, for example, the drain side, and only concentrate on energy variable. Then how does it look like? Then you can just find this kind of behavior. So are you with me? We are just to make a cut plane of this three-dimensional structure. Then if I can draw this position, the energy dependent distribution function at a certain position R, then distribution function can be written as or drawn as a function of energy. Please note that this is log 10 of our distribution function. Then you can see that there is a certain behavior like this. You can see that there is a very distinctive behavior. One is exponentially decaying behavior, and now you can see there is a deviation from this simple exponential decaying function, and this is corresponding to another effect. Then why quasi-Fermi potential is so important? Because this is quasi-Fermi potential, this guy can describe this majority part with only one single number, this quasi-Fermi energy level. So with this quasi-Fermi level, we can define this majority part, and this remaining part, this is not our concern or it's a concern. It just try to find out the majority electron or main body of electron gas. This is quite well described by electron quasi-Fermi potential, energy or potential. That's the reason why when we talk about the transport or modeling of our MOS problem, maybe you remember that we introduced the quasi-Fermi potential, and it played a really important role in our calculation. We say that at the source part it was fixed to 0, and drain part and it is fixed to drain voltage, and calculation of its variation within the channel was the main problem. Why it is so important? Because once we fix the distribution function, or once we fix the quasi-Fermi potential or quasi-Fermi energy, then it is corresponding to this main body of our electron gas. So most of its behavior can be described with this quantity. Then quite naturally, although quasi-Fermi potential is really beautiful and gives us the most important information, but it is also certain that it does not count this deviation from exponential decay. What is it? If we follow just conventional distribution, then maybe at this energy level we must have a quite a small number of electrons. However, in reality, we have much higher probability to have electrons. So this is really corresponding to hot electrons. For example, we expect that there is only just 10 to the minus 10 of probability expected from this Maxwellian distribution. However, now say that its probability is just 10 to the minus 7. It means that we have 3 orders of magnitude higher probability to have electrons at that point. So that is beyond our expectation, and we think that this is abnormal and something special and something to be noted, and it is called as a hot electron. So okay, so now when we have a certain hot electron or certain unusual electron, something happens. So something means that kind of these two slides just to describe two different phenomena. Don't be mix them up. So they are different. One is BTI. BTI is bias temperature instability. So please, what is bias temperature instability? Bias means that you apply very high bias to your transistor. What is high? For example, when you have an MOSFET, you apply VDD to your gate voltage. That is quite normal. So in the case of an MOSFET, you either apply 0 or VDD to your device. That is quite a completely normal operation condition. So now you apply VDD. Okay. Then temperature. In this case, temperature is taken as 100. The typical temperature is 125 Celsius. But you know, of course, this is elevated temperature. But please note that if you are interested with gaming, then every time a new CPU comes in, then some guys just to measure the temperature, and temperature is easily exceed or quite close to 100 Celsius. So 125 is not kind of course this is high temperature, not corresponding to 25 Celsius, but this is also within a range of allowed temperature range. So now it means that when you apply this how can I say severe operation condition, high gate bias. So high means that in the case of this MOSFET, now when you apply VDD, the electric field across the oxide region is quite high. In the case of PMOSFET, actually the things are the opposite. In this case, when you apply VG equal to 0 volt, then this is regarded as stress condition, because you know usually the source of our PMOSFET is biased to VDD. So in this case, our gate to source voltage is minus VDD. So gate oxide of our PMOSFET is also highly biased. So in both cases, although the actual value voltage itself is different for different devices, but it is certain that in this bias case, we try to apply high electric field in our thin oxide layer, and also temperature is intentionally elevated to, for example, 125 Celsius. In this case, what happens? So bias temperature means that the condition to apply stress. When this kind of stress is applied to our device, the result is this one. Instability. And instability of what? Instability of threshold voltage. So it is quite easy to understand. You buy your new chip. Wow, I spent, for example, $100 or several hundred $100 to build my new computer. And at first time, it works perfect. Wow, I'm quite happy. Now think about 10 years have passed. Then what you can expect is, inside your CPU chip, your devices were tortured during 10 operation years. It was applied to high electric field and elevated temperature. Then do you expect the same performance of your chip with the fresh chip and 10 years old chip? So of course you expect certain degradation of the performance, and degradation comes from change of our threshold voltage. Of course, change of threshold voltage is not the only symptom of this degradation. For example, reduction of mobility itself is also quite a big deal, because we have more defects generated inside our system, so mobility is also degraded. But most important one is the changing of our threshold voltage. Usually the tendency is the absolute value of our threshold voltage goes up. So previously the device was well turned on and turned off. However, after 10 years later, in a severe experimental or operational condition, then it does not conduct as expected, because the threshold voltage, its actual threshold voltage is increased in terms of its absolute value. So at a given VDD value, it is not strongly turned on. Please have a look at this one. This is taken from IDM paper already 7 years ago, but the general trend is more and less the same. So sorry, because since I took it from the paper, so the y-axis is missing, but it should be regarded as just absolute value of delta V compared with the brand new chip. So just fabbed out from our manufacturing procedure. Now we measure its threshold voltage. Well, I have a certain number. After that, we intentionally apply stress and measure its threshold voltage. Then there is a tendency. Please have a look at this number. Oh, so sorry about that. I think that this is corresponding to, if I remember correctly, this number is corresponding to 0.1 volt. Well, and there is another one corresponding, yes, this is corresponding to, oh yes, this is no, sorry about that. This is corresponding to 10 millivolt, and this is 0.1 volt. It means that now, think about this one. Here we have target. Target means that this is the acceptable range of a threshold voltage shift, and this value is maybe corresponding to 5 millivolt. And this means that in order to have successfully working technology, when we apply our device, for example, this is corresponding to 0.7 volt to our N MOSFET. You know, 0.7 is corresponding to the VDD of recent technology. We apply VDD and increase the temperature up to 125 Celsius and just to wait. Then what will happen? Then how about the drain condition? In this case, drain bias is equal to the source case. So there is no current conduction through the channel. Channel is just having electrons, and only stress is applied across this vertical structure, gate, oxide, and channel. So therefore, in this case, stress happens only vertically, and in this case, even after a certain time period, we just wanted to have just 5 millivolt difference in its threshold voltage. So it means that even though we just operate this device in a quite severe environment, our threshold voltage should not increase quite high. 5 millivolt difference is just 0.005 volt. So that is the acceptable range of our technology. Of course, this quantity is not for only single device. We must think about billion devices, because we are currently fabricating billion devices at the same time in a chip, and they are operating in the same condition. So after that, some guy can show higher delta VT, and some guy can show relatively low delta VT, but always the worst case determines the scenario. So we must keep the worst case. Worst case means that the maximum deviation of threshold voltage as much as possible. So simply this experimental data shows that, well, previously, according to their article, at the starting point, this was their initial technology. At initial technology, their device can show more than 0.1 volt difference in the threshold voltage in the same stress condition. But by doing some clever tricks to improve their gate stack, they were able to reduce the values of their delta VT. So now it is now fitting the target for our reliability condition. So I just mentioned a very important keyword called as reliability. Reliability means that after long time of operation is over, still your chip must work as a normal working chip. So for example, every chip manufacturer should guarantee that your chip or our chip is working at least 10 years. So please believe me. After 10 years, there is no warranty. So I don't know, maybe it failed. So never care about that one. However, if your device, many of your device fails before the given warranty time, then it is related with industrial claim. Your customer call you and your device has some problems, so therefore we should buy our customers. Also these guys has customers, so that introduce actual failure or big business loss in a company. So reliability is typically very difficult to detect, because it is only detected after 10 years later. You sell your chips after 10 years later, or a few years later, your chips start to fail. Then what will happen? It is very difficult to imagine the business loss. So therefore what they do is this one. Why do we need elevated temperature? Elevated temperature accelerate the failure mechanism. So therefore, without waiting for 10 years, we introduce this severe condition, and just this exaggerated stress condition to our device, and it can fail quite quickly. Then since our normal operation condition is not 125 Celsius, so let's try to just fit it to normal BIOS condition. Then maybe it is corresponding to 10 years of warranty. That is the way we do this reliability concern. This is an important part of electronics research and development. Always when we visit research components, there are so many different sub areas of this research activities. The most the front one is, for example, introducing new material or new architecture, so they can get certain highlights. However, please note that the main body of our engineering work is related with the successful working of our fabricated chip. Say that you fabricate 100, so in your lab, you fabricate 100 devices, and one of them shows world record behavior. So you publish a paper, great, in R&D case. However, if it is really working in the industry, now we must introduce several billion transistors, and it should survive 10 years. Then there is a huge difference between this dream and industry reality, and actually this reliability is the key part to keep our industry alive. Without this reliability issue, nobody will buy an electronic chip, because, well, a few days later, my cell phone gone, and everybody said that it is completely normal in the electronics. Please buy another one. So we cannot live with that, such a world. So reliability is a really important one. So I think that I have stressed the importance of reliability quite a lot, and among many reliability issues, actually in current VLSI devices, this BTI is the most important one, and that's the reason why I just bring this BTI. And depending on their BIOS conditions, we further divide them into two parts, NBTI and PBTI. NBTI means that our applied BIOS is negative, and PBTI means that positive. So simply speaking, in the case of MOSFET, we call it as PBTI, and in the case of PMOSFET, MBTI is important. And important point is, it is always related to the specific technology. For example, actually when you just read the Professor Tower's second edition, it is say that the book says that only MBTI is important. MBTI in PMOSFET is important. And what is the current situation? The current situation is now at least they are equally important, or even PBTI in MOSFET is important. Why? Because we have changed our gate stack and improved the process steps. So depending on small change in our fabrication process, that reliability severely impacted. So in former time, when we had planar MOSFET, so MBTI was the only problem. Nobody cared about PBTI. And after that, people said, oh, PBTI is also important. And nowadays, PBTI is sometimes more important. That is current situation, and nobody knows what will happen if we introduce new technology. So that's the problem. Once we introduce new technology, IV characteristic, it's good, but we must be careful its introduction to the industry. It should survive for 10 years with very extreme conditions. Only after that we can sell it to our customers. Otherwise, they will refuse to buy. Okay. So then, what is the physical reason of this reliability issue? And it is known that yes, interface trap generation. Up to now, I intentionally to talk about traps as much as possible. I think that I'm quite successful up to now, and now it's time to talk about trap. So trap, trap. In an English word, trap means that there is an animal, and in order to capture it, we make a certain artificial structures. And for example, cheese from a mouse, then it is just captured. Just like this, trap in this context means that trap for our electrons and trap for holes. Then what is the capture? In this context, we believe that if electrons are moving in conduction band, it's free. If holes are moving in the valence band, if it is found there, then we say that it is free. But so please note that this drawing is already assuming this vertical energetic axis. So here we have a conduction band minimum and valence band maximum. And when we have electrons and holes there, then we think that this is free. Just like a mouse hanging around the floor. And now we introduce an electronic state, which is found in the forbidden zone. And now this one, let's say that this guy is empty, so there is no electron, and let's say that this electron, let's assume that this electron can lose its energy by generating several phonons. There is a mechanism to lose its energy, and now it becomes a lower energy electron and transit into this position. Then now think about this one. Previously, there was an electron hanging around. But now this system is really localized. It does not move freely. It is localized at a certain position and it loses its energy. Then we say that, oh, an electron is now trapped. So that's the reason why we call this energetic state, the electronic state, as trap. Then how can we generate, or actually nobody wanted to have traps in our silicon material, so we wanted to avoid this trap. However, unfortunately, it is not possible to completely remove traps. So unfortunately, every time we must have trap at inside our device. Then what is the physical structure to generate electronic trap? This is corresponding to, many people say that in the case of a silicon dioxide layer, then there is a silicon and oxygen, and they are connected by their bonding. And for some cases, so there is the bonding broken. So silicon, and it is connected to other silicon and or oxide, but let's assume that one silicon bond, this bond is not connected with other surrounding atoms. In this case, now instead of making this connected to other atoms, it can capture one electron or once again release this electron. So usually people say that this kind of physical structure is the physical origin of interface trap. Then why do we have dangling bonds? And why its number or density is increased by applying stress, for example, by applying MBTI and negative bias temperature stress, why we have instability? Then maybe the possible reason is now we have elevated temperature. It means that all of our atoms inside our devices are dancing. At room temperature, they are just staying. But since we are elevated the temperature up to 125, and themselves, atoms themselves are summarily excited. So they are easy to move in this case. And now we apply high electric field. And atoms, their cores are ions. And they feel the field. Oh, I have sufficient energy, and there is a strong electric field. So some of our atoms are moving, following the electric field. So say that at the initial state, when we make a fresh device, we try to our best to passivate our silicon dioxide layer. So therefore, the number of dangling bonds is minimized. However, when you apply this stress condition, bias temperature stress, in this case, atoms are summarily activated and they feel strong electric field, and some of them are just swept away from the initial position. So we have some empty places for atoms, and that is regarded as a physical origin of interface trap generation. But I wanted to be very careful, because the exact physical mechanism of this BTI is still of active research deviate. They are really fighting. So there are some research groups say that this is the most important reason, and some other guys say that no, this is the most important guys. And I'm not in that debate. I'm a little bit away from that debate and just watching them fight in every international conference. So still, it is, although BTI itself is well known and every related researchers can measure it. So there are tons of data. But problem is, this is so sensitive to the fabrication condition and measurement conditions. So there is no definite model for this universally explain all kinds of measured data. So that's the problem. So for example, as the time elapses, how fast this threshold voltage instability increases. So this is quite a basic question. However, still, in the case of a measurement and in the case of a theory, there are no globally universally accepted theory. At least from my point of view, if you meet some guy actively working in this reliability issue, then he or she will certainly say that, oh, our group solved every problem. We can solve every issue. But frankly speaking, I'm not quite an expert on this issue, so I wanted to be a little bit more objective. This is practically one of the most important problem. However, very difficult to solve this problem or address this one or improve this one. So this problem isn't when you solve this reliability problem, but your work is not advertised as on research paper. Although this is the key contribution for success of your technology in an academic sense, it is not highly recognized because this is top secret how you improve your technology. And since other competing companies have all the same problem, so this is a little bit like an unsung hero in our VLSI industry. Okay, and you know that in order to talk about this interface trap generation, we must understand the physical mechanism. But in the case of a physical mechanism, maybe the initiator of this interface trap generation is regarded as high energetic electrons. So high energetic electrons hit the weak structure, and that is regarded as the initial step to generate the defect state inside it, and it is quite much related with this energy distribution function. We must know that how many hot electrons are there. Of course, hot electron itself is not the only single reason, but we know this distribution. Another one is breakdown. What is breakdown? The breakdown here means that it's like usually what we know is like this. ID and VDS, and when we apply certain drain bias, then it is increasing and saturated. Of course, we have a slight finite slope, and this is corresponding to the short channel effect or something like that. But anyway, it is true that we expect such kind of behavior for our MOS transistor. Then the question is, what is this value? So usually what we apply is just VDD. Up to VDD, we expect such kind of a behavior. Good. But what happens if we exceed this predefined VDD value? No, never do that. Yes, that is a recommendation. But what happens if we apply, for example, 1 volt higher than VDD, 2 volt higher for VDD? So the answer is okay. Still beyond this VDD, it just try to behave normal device. But when we have a certain voltage value, usually called as breakdown voltage, BV means that a breakdown voltage, and now its current value just vertically increase. So why it is vertically increase? It means that now just small voltage below this breakdown voltage, the current level is quite much acceptable. However, when we increase a little bit in terms of its drain voltage, now it becomes very high. So what is it? The physical mechanism for this kind of behavior is like this. Now electrons are moving. Yes, electrons are moving, and when we apply too high VDS, now what we can expect is, the energetic difference between this source side and drain side is directly corresponding to Q times VDS, and now this energy level is so high. So what? So when we have such a high VDS value, then now many of our electrons fail to its energy. So it means that there are so many hot electrons. Yes, the generation of hot electrons already studied in our previous lecture. So what is the importance? The importance is when its kinetic energy exceed the band gap of our silicon, then now there occurs another phenomenon. Now let's say that, of course, this generation of a hot electron is quite a low probability event. Among many electrons, some of them becomes hot and happen to be its energy is exceeding the silicon's band gap energy. Then the next part is this hot electron just to transfer its kinetic energy to an electron inside valence band. So simply say that, let's say this is band gap energy, and consider an electron whose kinetic energy is also band gap energy. In this case, what happens is, now this electron just transfer its entire kinetic energy and just becomes cold electron. Then what happens to this lost energy? This lost energy is now used to move one electron originally located in the valence band into this conduction band. then please think about the consequence of this transition. The original electron is just to become a cold one. That does not change the electron number. However, the second effect really makes something. Now there is one electron newly generated by taking this energy, and there is one hole or left empty space. Simply speaking, when we have a hot electron, this one becomes a cold electron and a secondary electron and a secondary hole. That is the effect of this hot electron. When you have a hot electron, of course, there is this transition is not 100% sure. It means that also this transition occurs probabilistic way. So there is a certain extremely low probability. But anyway, let's assume that specific event happens. Now, initially you have one electron, but now you have two electrons, and these two electrons are once again accelerated, and these two electrons becomes once again hot, and they generate once again secondary electrons. Then what will happen? Now we will have 4. Now we will have 8. Now we have 16. So starting from one electron, if it can double its value during its journey, then what will happen? We will have tons of electrons generated from this one single hot electron. So that's the reason why now we have quite a rapid increase of this current density. So maybe you can ask me this question. Actually, you must ask me this question. Then what is the destiny of this secondary hole? When a secondary hole is generated, and for this secondary hole, source or drain, highly n-type regions are not attractive. It should be consumed by the substrate, p-type substrate. So it just goes to the p-type substrate. So in the case of a planar MOSFET, this is a simple way. But unfortunately, we have also different technology called as SOI devices, silicon on insulator technology. In that technology, we don't have substrate. Then one secondary hole is generated. It cannot find the right position to be consumed. So it just to move long way, eventually consumed by a certain contact. And it can introduce some problems in its device operation. So if you have not heard about SOI, of course we will revisit this structure once again. However, what I wanted to say right now is, in the case of a SOI device, there are two different types. One type is fully depleted one. Another one is partially depleted one. So fully depleted, partially depleted. What is the difference is, in the case of a SOI, you just buy SOI wafer from company. There are specialized company who generate these SOI wafers, and depending on the thickness of this silicon region, the device can be used as a fully depleted one. This means that very thin one, and partially depleted one, this is a thick one. In the case of a partially depleted one, especially this secondary hole generate a lot of problems, a lot of instability. So unfortunately nowadays we are able to fabricate this SOI type devices with different ways. So well, anyway, so let me just wrap up today's lecture. Today we'll talk about quite important quantity called as energy distribution function. This simply means that at a certain position and energy, how much it is probable to be occupied. This is the concept, and with this distribution, the additional information what we can expect from this distribution is not just the number of electrons, but how many electrons are hot. That information is obtained by this distribution function, and using these hot electrons, they introduce many usually unwanted behavior. This reliability problem or this breakdown voltage, many kinds of this effect is related with energy. One, but please be careful. Then I'm afraid that after this session is over, everybody thinks that, oh, hot electron is a bad guy. We have to reduce hot electron one. But for some applications, they are used to, for example, cure defect or program our NAND devices. There are other applications. So it is not always bad, but in many cases, it introduces bad impacts on our VLSI operation. Okay, thank you, and see you next Monday.